Hi, you guys. I thought I'd make a few quick videos on what you're going to be looking at Khan Academy. I'm a little concerned because you guys don't have the calculators that maybe you need, so I'm hoping that I can find something on the web that will help us determine some of these values. I haven't started looking at, which maybe I should have started before I post this video, but I'm going to talk through it, and then I'm going to see if I can find an online thing that will work for us, okay? So we're going to be start looking, those words didn't even make sense. We're going to start looking at the same exact thing that we've been doing, which is inference, meaning our z-scores and our t-scores, and finding a p-value, and what does that p-value mean, and blah, 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 blah. But this time we're going to do it with two samples rather than one sample, which is what we've been looking at, okay? So I'm just going to kind of start talking through this. Again, you have the Khan Academy videos as well, but I did want to add a little, of my words into that as well. So starting with the two-sample inference on procedure with means, and I'll post this lesson so that you have the lesson too and not just this video. So when we look at a two-sample procedure with means, the goal here is to be able to do the inference procedures, but this time to be able to either compare the responses with two different treatments or to compare the characteristics of two populations. So we can really think about two sample either way. We just want to make sure that we do have independent samples from each treatment or from each population. So we don't want there to be any dependence on the two groups, okay? So starting off, and I'm not going to do the math behind this because I don't think it's relevant for you guys. I always think it's relevant, but I do think that there's time better spent. So really quick here, it turns out that you can, here we go. You can find the mean of two populations simply by, when we're comparing the two, simply by just subtracting them. So like if I wanted to find the mean of x minus y, it would just be the mean of x minus the mean of y, exactly like what you expect it to be. But if you look at your formula sheet, your AP Statistics formula sheet, you're going to find that the standard deviation of the difference between two proportions, or two means in this case, is not just standard deviation minus standard deviation. It is not just standard deviation minus standard deviation. It is actually the square root of the square of the two standard deviations. Looks a lot like Pythagorean theorem actually, right? A squared plus b squared, and then take the square root. But and just keep in mind though that when you're looking at your formula sheet, and maybe I should pull that up. If I could pause, I would. Oh wait. I paused and I found it. So I've got it right here. You can see, I hope that for two populations, so I'm in this sampling distributions and inferential statistics here, that if I want and I'm in means, so that'd be x bar. If I want for two populations x bar minus x bar, the mean is just subtract them, but the standard deviation is that standard deviation squared plus standard deviation. And of course, this is for a sample, okay? I'm on the sample page. I might come back up this new formula sheet, man. I just don't have it memorized yet. Nope, I think that's where you're going to find it. Okay, so the difference here being that this is for a sample and this is for, of course, a population. Okay. So, I don't know how to go back. Oh, there we go. All right, so a really quick problem here. Suppose we have a population of adult men with a mean height of 71 inches and a standard deviation of 2.6 inches. So can you imagine this curve here? This curve. And then we have a population of adult women. Mean height is 65 inches, so smaller, of course, because we're women. And a standard deviation of 2.3, meaning we don't deviate as much from our mean. Assume the heights are normally distributed, really important. Describe the distribution of the difference in the heights between males and females. So difference means subtraction. So if we want to find the mean, then we would subtract 71 minus 65, and we would get 6. I think it's better actually with all these words if I am using this highlighter tool. Well, here we go. So if I'm wanting to find the difference, then I can just subtract 71 minus 65, and that's where that 6 inches is coming from. But if I want to find standard deviation, and I think you could see this, take a second, because if I subtract 2.6 minus 2.3, that's 0.3, which does not match the standard deviation. And we wouldn't expect the standard deviation, guys, to shrink so small, right? We just wouldn't expect that, and it wouldn't happen. So I would square this, square this, square this, add them together, take the square root, okay? And that would give me this standard deviation. If I graph that, so here's my female and my male together, and then we subtract them, we end up with this curve right here with a standard deviation of 3.471. And our mean is, I'm pointing at the screen like you can see that, right here in the middle when I subtract 71 minus 65, okay? So part A says, and we're talking about this graph right here, so I'm going to see if I can keep this together here. What is the probability that the height of a randomly selected man is at most 5 inches taller than the height of a randomly selected woman? So the average is 6. We want at most, meaning the largest, to be 5. So if I grab a color here, right, if my standard deviation is 3, then one standard deviation would be 2.5-ish. Now I'm just estimating, and I'm not doing a good job of writing either. 6 minus 3.471 is approximately 2.5, right? So 5 is going to be, like right here. And so I'm talking about this area right here. And this is where it gets a little wonky, right? Because if I had a calculator right now, I would say, let's go to normal CDF and find our information. We would say my lower bound is negative infinity, or negative 999999999, and my upper bound is 5, right? So that's the at most 5. And my mean is 6, and my standard deviation is 3.471. And when I type that in the calculator and I use my normal CDF, my area is about 0.3866. Or we would say the probability that a height, or the chance that the height of a randomly selected man is at most 5 inches taller, would be about 38%. Which, if I just look here, I would expect it to be just a little under 50%. So 38% makes sense to me. Okay. Okay, let me get rid of that sucker. Now, my next question says, what is a 70th percentile for the difference in heights of randomly selected? So this time, I'm looking for 70% on this curve. Now, that means I've given you the p-value. I've given you the area, and you have to find the z-score, okay? So now, I said z-score. Z-score if we're on the normal curve, but we're going to leave it on this curve. So what would be on this axis, okay? So basically I'm saying I want to know where the area is 0.7 in here. Well, here's 50%. So we know we've got to go out quite far, because one standard deviation is 68% on the inside, right? On the inside. But we want 70%. Wow, like this, right? I don't know where it's going to be, something like this, but all this colored in. And then the question is what would this number be, right? And so I could sit here and I could do normal CDF and just sit here and guess what this upper bound would be, right? Because 5 was 38%. So then I would try 6, 7, 8, 9, 10. Then I'd have to try some decimals to get closer. Okay, but we have a calculator function that does the inverse of what normal CDF does. And that calculator function is that inverse normal, where it says, okay, give me the area that you want, give me the mean, and give me the standard deviation, and I'll tell you where you should be, okay? So if we type that in, 70% or 0.7, mean of 6, standard deviation, we get 7.82. Does that make sense for our problem? And it does. It does make sense, right? Because we expect it to be over here. And we could check that by taking 7.82 and typing all this in again, but replacing this 5 right here with that 7.82, and the answer I should get back out is 0.7. Okay. So you can see that's all exactly the same, except we're looking at the difference between the two. Okay. Again, this was meant to be taught with a calculator in hand, so I'm going to talk through it and hope it makes some sense. Okay. So it says, what is the probability that the mean height of 30 men is at most 5 inches taller than the mean height of 30 women? I have a whole thing set up for this. So we're gonna skip this, sorry, because I don't have it here. Okay, so here are our assumptions. Where our assumptions are that we're gonna have 2 simple random samples. We have to, for the populations. And that each of those simple random samples were, or I should say, wow, we're either going to have 2 simple random samples or our treatments that we're going to do are randomly assigned, okay? So like men and women randomly selected, or I've got a group and I'm randomly selecting 2 treatments to that one single group, okay? Then that kind of naturally splits it into 2 groups. Both of the distributions are approximately normal, meaning that they have enough large enough sample size, we're talking about means, or you graph both sets of data and it works out. If our standard deviations are known, great, we'll z-score. If our standard deviations are not known, crappy, we'll t-score, okay? Remember, z-score, t-score. We know both. Okay. If we're going to t-score, then we are going to have to know degrees of freedom. And so this is yucky. Degrees of freedom for the difference between 2 groups is not straightforward, right? Because you got 2 groups you're talking about. So n minus 1 is a little confusing because you have 2 n's. And so the safe choice and the way that I would always recommend is find n the first groups, the first samples, n minus 1, and the second one's n minus 1, and then use the more conservative, okay, which is the smaller one. Option 2, you can use a calculator to find it. This is the formula. Let's just do this one. Okay, if you're doing a confidence interval, then this is your new formula. So sample mean minus sample mean plus t-star, none of this changes except for we're subtracting them now. And our new standard deviation is sample standard deviation over squared over n, the first n, and then second standard deviation squared over second n. If you have 2 populations that have the same variance, which is not normal, when you pool, this is what it's called, when you pool, you average the 2 sample variances to estimate the common population variance. But don't do this. It exists. It's a thing. If you're Googling stuff, it's going to come up. So I didn't want to mention it. I did want to mention it. But for us, for this class, we're not going to pool. Okay. Wow, this looks crazy. Let me pause this. Hang on just a second. Okay, I'm about to disappear for a second because I pulled this up on a Google slide so that maybe it'll make more sense. So hang on just a second, and I'm going to put us into a presentation mode. Okay, so this is actually what that's supposed to look like. I'm not sure why my 18.9 split like that, but all right, it says 2 competing headache remedies claim to give fast-acting relief. An experiment was performed to compare the mean lengths of time required for bodily absorption of brand A and brand B. Assume the absorption time is normally distributed. 12 people were randomly selected and given an oral dosage of brand A. Another 12 were randomly selected and given an equal dosage of brand B. The length of time in minutes for each drug to reach its specified level in the blood was recorded, and the results were followed. So you got a mean 20.1 minutes for brand A, a standard deviation, and a sample size. And then you have brand B, and it's 18.9 minutes, and a standard deviation of 7.5 minutes, the sample of 12 people. Okay. It says describe the shape and standard error for sampling distributions of the difference. So we would, just like we did on the previous one, we would just do 20.1 minus 18.9 for your mean, and your standard deviation would be that A squared plus B squared square root of that. And that would give you your shape and standard error. And so, too far, sorry. You would look something like this, normal distribution with, and I didn't write the mean down, but that's our standard error. Okay. Then it says, given 95% confidence interval, difference in the mean lengths of time required for bodily absorption. Okay. So that is your X bar minus X bar plus your T or your Z times your standard error. Okay. We're going to use T because we don't know anything about the populations. All we know is sample. So X bar minus X bar plus or minus T star and our standard error. And so, and then we have 21.53 degrees of freedom. If we use our calculator to determine the degrees of freedom, it is safe for you to use 11. That is fine. And when we plug our numbers in, we get an interval that's something like this, okay? Again, that's a calculator degrees of freedom. Make sure you're writing your conclusion in context. This looks insane. I'm going to delete. So I really want, let me get rid of this. And I'll get rid of this. There we go. The responsive core sounding something like we are 95% confident that the true difference in mean lengths of time required for our bodily absorption of each brand is between these two values. Okay, so obviously it's not going to be negative 5.685 minutes. That doesn't make any sense for it to absorb before you take it, but the mean difference between the two, then you could include those negatives. Okay. All right, so when we are looking at, and this is a little confusing, but when we're looking at confidence interval statements, match pairs, which is what you did in your project, and also what we did, we've done match pairs a few times now, it's a mean difference. And what we're looking at here with a 2 sample is a difference of means. So when you did your matched pairs, you actually subtracted every single value and did everything based on that one column, right? You subtract, 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 and you do all your math based on one column of data of the subtractions. But when we're doing a two sample inference, you're actually getting a mean for one and a mean for the other, and then you're in a standard deviation for one and a standard deviation for the other, and then you're subtracting, right? So there's a difference between the mean difference, which is I take a difference and then I find the mean of it, and the difference of means, which means I find a mean, and I subtract them. Okay, that's the difference. Okay, so I'm trying to see what I want to go to next. I just don't want to talk. I think just in terms of our what you're doing on Khan Academy, you probably have enough to go on. So I'm going to stop there for now, and I'll pick back up later for proportions, okay?